Hello everyone. I'm going to go over some of the most requested problems from the Unit 5 test review. So if you want to have that out in front of you and a calculator, I'll go over some of the problems that you asked for. If we look at this very first page, this is just like what we did the very first day of notes. So if you look at your day 0 compare and construct notes, we had 3 graphs and we went over very similar characteristics, and your homework was also very similar. So that day 0 notes and practice assignment will help you with this first page. So let's make sure you can graph all 3 of these. If we look at number 1, this one is going to be linear. And I know that because it has a degree of 1, meaning the highest exponent is 1. This one is of the form y equals mx plus b. Let me make my marker a little skinnier here. So I know that b is 0, and that's my y-intercept. And my slope is negative 3. So I'm going to go down 3 and to the right 1. Down 1, 2, 3, right 1. 1, 2, 3, right 1. I could also go up 1, 2, 3 and to the left 1. 1, 2, 3, left 1. 1, 2, 3, left 1. And then I can connect my points in a line. Hopefully when you do it, your line is a little bit better than mine. If you do not remember how to graph this stuff, I highly recommend that you go back and you look at your Unit 2 notes. We learned how to graph linear equations back in Unit 2. So going back and refreshing your memory on linear equations will really help you with Unit 5. On number 2, this one is exponential. I know that because the variable x is an exponent. So whenever a variable is an exponent, it's exponential. To graph these, we learned to make a table of values, and we typically did -2, -1, 0, 1, and 2. To get the corresponding y values here, you can either plug these values in for your exponent and get the number that way, or you can use a table feature in your calculator and copy them down. Again, if you do not have a graphing calculator at home, there is a free graphing calculator app called Calculate 84, all one word. It looks identical to the ones that we use in class. So if I just plug in 3 to the negative second power is 1/9, 3 to the negative first power is 1/3, 3 to the 0th power is 1, 3 to the first power is 3, and 3 to the second power is 9. So I'm going to go ahead and pause the video and plot those points. If you haven't plotted them already, go ahead and feel free to do the same. So here are those 5 points that we came up with. Remember that we learned that we cannot graph an exponential function until we have the asymptote. Remember, your asymptote always comes from your k value, because remember this is of the form y equals a times b to the x minus h plus k. K is your asymptote, it's that number on the end here. Here I don't have a number on the end, so it's like it's plus 0. So I know that my asymptote is at y equals 0. This is a line that my curve gets very, very close to, but does not cross or touch. When you connect these points in your curve, it will look like this. Again, we get very close to that asymptote, but we do not cross or touch it. And again, if you're struggling with exponential functions, I highly recommend that you go back and review our Unit 3 notes. Unit 2 and Unit 3 were done in our first semester. All of my first semester material is in the milestone folder, so you can go back and look at that stuff as needed. Lastly, we have a quadratic function. This is what we learned in Unit 4. There's a couple different ways that you could approach to graphing this equation right here. You could recognize that it is either in standard form or vertex form. My bet is that a lot of you are going to see this in standard form. To graph something in standard form, we learned to find the x-coordinate of the vertex first. To do that, we did negative b over 2a. Here, b is 0, and here, a is negative 3. So I'm going to have 0 divided by negative 6, which is 0. So I can make a table of values here. And let's see, 1, 2, 3, 4, 5. So 0 is going to go in the middle of my table. After 0 comes 1, after 1 comes 2, before 0 is negative 1, before negative 1 is negative 2. From here, you can either plug in these values in for x to get your corresponding value for y, or you can plug it into your calculator and copy the table of values. If you haven't done it yet, go ahead and pause the video and complete the table of values and graph your function. When you graph this, you will see that you have a parabola. We knew it was going to be upside down because my a value is negative, and that tells me that it's a reflection. Now that you have all three graphs, you should be able to go through and answer all of these characteristics. These characteristics, we've been doing all of these since Unit 2. So if you're struggling with any of this stuff, definitely go back and for sure look at the 2.7 notes. I think we had 2 days on that, and it went through all the different characteristics of linear functions, and those same characteristics apply to exponential and also apply to quadratic. You're definitely going to need to go back and review those notes. I'm going to go over some of these with you. Give me just a second and I'll meet up with you here in a minute. So if we look at the slope over the interval from 0 to 1, this is telling you to find the slope between when x is 0 and when x is 1. Make this smaller. So when x is 0, that's right here, and when x is 1, that's right here. To find the slope, I can do rise over run. So I'm going to go down 1, 2, 3, and to the right one. So my slope is negative 3 over 1, which is negative 3. Then it wants me to find the slope over the interval from 1 to 2. So now from 1 to 2, well, we said 1 was here, and now 2 is here. So now I'm finding the slope between these 2 points. Again, I'm going to use rise over run. So I'm going to go down 1, 2, 3, and to the right one. Negative 3 over 1 is just negative 3. X-intercept is the point on the graph where it crosses your x-axis. That's this point right here. That's the point 0, 0. Your y-intercept is a point on the graph where it crosses the y-axis. That's right here, and that's also at the point 0, 0. Interval of increase and decrease. This is when you trace your graph from left to right. When I trace this graph from left to right, it is going down. So I am decreasing the entire time. I'm decreasing over my entire domain. My domain is going to the left forever, so that's at negative infinity. And it's going to the right forever, so it's going to positive infinity. So my domain is from negative infinity to positive infinity, and my line is decreasing over that entire domain. Just like how you read a book, that's how you read a graph. From left to right, this graph is going down the entire time. It's never going up. So I do not have an interval of increase, so this is none. Positive and negative over the interval. Again, when we're talking about positive and negative intervals, we're always talking about your x values. So we're saying for what x values are your y values positive, and for what x values are your y values negative. Your graph is always positive above your x-axis because this is where your positive y values are. Your graph is always negative below your x-axis because this is where your y values are negative. So we're positive above the x-axis and we're negative below the x-axis. So I am positive. I'm going to the left forever. My x values are getting more and more negative the further to the left that I go. So we start off at negative infinity. And I'm positive up until my x-intercept. So I'm positive up until when x is 0. 0 is a point of change. At 0, I can't be both positive and negative at the same time. Because of that, 0 is going to get a parenthesis. I'm negative starting at 0, and again, because it's a point of change, it's going to get a parenthesis. And I'm going to keep being negative forever. This is going to the right forever. My x values are getting more and more positive, so this is going to positive infinity. So increase and decrease, positive and negative, you're always talking about your x values from left to right. Increase or decrease, you're tracing it from left to right. If it's increasing, you're going up. If you're decreasing, you're going down. Positive and negative, you're saying for what x values are your y values positive. That's always going to be where your graph is above the x-axis. For negative, it's saying for what x values are your y values negative, and that's always going to be below your x-axis. End behavior. As x approaches positive infinity, this is telling you to look at the right side of your graph. The right side of my graph is going down forever. Y values are going to negative infinity. As x approaches negative infinity, this is telling you to look at the left side of your graph. The left side of your graph is going up forever. Your y values are going to positive infinity. Asymptote. This is a linear function. Linear functions do not have an asymptote. Growth or decay. That's for exponential functions. Linear functions do not have growth or decay. Vertex. That's for quadratic functions. Linear functions do not have a vertex. Now that I've done number 1 for you, go ahead and try number 2 and number 3. Again, we've practiced all of this stuff in each of their respected units, as well as on those day 0 notes and those day 0 practice. So go back, look through your notes to help you complete this section. The next group of questions that I was asked to look at were questions 8 through 13. This is what we did on the day 1 notes when we learned how to identify whether a table was linear, exponential, or quadratic. So that's how you could get help with 8, 9, and 10. 11 through 13, this is applying the knowledge that you learned in units 2 through 4. If I look at example 8, I can see that example 8 is going to be exponential because it has a common ratio. To go from 1/9 to 1/3, you multiply by 3. From 1/3 to 1, you multiply by 3. 1 times 3 is 3. 3 times 3 is 9. Number 9, to go from 6 to 3, I subtract 3. To go from 3 to 2, I subtract 1. To go from 2 to 3, I add 1. And to go from 3 to 6, I add 3. To go from -3 to -1, I add 2. To go to -1 to +1, I add 2. And to go from 1 to 3, I add 2. Here, my second difference is the same. Because my second difference is the same, that means that example 9 is quadratic. Example 10, to go from -3 to -1, I add 2. -1 to +1, I add 2. From 1 to 3, I add 2. And from 3 to 5, I add 2. Here I have a common difference. My constant rate of slope is the same. So here this is linear. And again, there's a whole video going over all of these rules in your Unit 5 folder. Now it says write an equation that models the relationship for the table in number 8. There are so many different ways that you can think about this. I'm just showing you one way. We learned so many different equations, and in math you can do things a million different ways. So this is one way that you could think about number 8. Since I know it's exponential, I could use the formula y equals a sub 0 times r to the x. I know that a sub 0 represents the y-intercept. And I can see the y-intercept in my table of values. Because remember, your y-intercept is always when x equals 0. So I know that a sub 0 is 1. Earlier we said that my common ratio is 3 because I'm multiplying by 3 every time. So my equation would be y equals 1 times 3 to the x. Number 12 is quadratic. Again, you could think about any of the forms when you try to do this. Because I can easily see the vertex here, and I know that this is the vertex because my values start to repeat around it, I'm going to think about vertex form. So we learned y equals a times x minus h squared plus k. So here I'm going to have y equals, I don't know what a is, so I'm going to leave that blank for right now, x minus 0 squared plus 2. Because remember, 0 is h, and 2 is k. I'm just plugging in for h and k in the formula. Well, I can simplify this a little bit, right? X minus 0 is just going to be x. So I'm going to have y equals x squared plus 2. Now, we weren't sure about the a term. So what I'm going to do now is plug in for x and see if I get the corresponding y. So negative 2 squared is 4, plus 2 is 6. That works. Negative 1 squared is 1, plus 2 is 3. That works. 0 squared is 0, plus 2 is 2. That works. 1 squared is 1, plus 2 is 3. That works. And then 2 squared is 4, plus 2 is 6. That works. So it looks like here our a value was 1. And I had to figure that out just by guessing and checking. So my equation for number 12 is y equals x squared plus 2. Again, this is just one way that you could think about number 9 in writing it as an equation. Same thing for 13. Whenever we think of linear functions, 9 times out of 10, you guys tell me slope-intercept form, y equals mx plus b. B is your y-intercept. I can see my y-intercept from my table because it's always when x is 0, so b is negative 1. My slope is 2 over 1, which is 2. So my equation is y equals 2x minus 1. Again, lots of different ways to think about these 6 problems. Maggie is collecting pine cones from her yard. On the first day, she collected 100 pine cones. On the second day, she collected 50 pine cones. On the third day, she collected 25 pine cones. So right now I know on the first day, 100, second day, 50, third day, 25. If it helps you, keep going with your table to recognize the pattern. Here it's asking for an explicit equation. When we talked about explicit, we were talking about arithmetic sequences and geometric sequences. When I see this pattern, here I'm cutting it in half every time. So when I do that, I know it's a geometric sequence because we're multiplying or dividing every time. If you look at your formula sheet, your explicit formula for geometric sequences is right here. And so that's the formula that I'm going to be plugging into. And so I'm going to have a sub m equals, my first term is 100. And then to go from 100 to 50, I'm multiplying by 1/2. From 50 to 25, I'm multiplying by 1/2. Remember, whenever we're plugging into the formula for r, we're always talking about multiplying, not dividing. Because if I said 2 here, then that would be meaning that I'm doubling every time instead of cutting it in half. So r is 1/2, and that's going to be the n minus 1 power. Then it wants to know how many pine cones Maggie will collect on the 5th day. Two different ways that you could do this. You could say, okay, n equals 5, and then you could plug into the formula that we just created. So I'll have a sub 5 equals 100 times 1/2 to the 5 minus 1 power, and you could do that in your calculator. Or you could keep going with your table and doing it that way. Either way, both of those methods work. When you do that, you get 6.25 pine cones. On number 15, a tree has 100 branches on its lowest level. Each level up has 3 fewer branches. What level has 67 branches? Again, this goes back to what we learned about sequences. Here I can tell that this is an arithmetic sequence. I know that because I'm subtracting 3 every time. Whenever you're adding or subtracting, that's something that's linear, and so it's something that's arithmetic. Again, highly recommend that you go back and look at your Unit 2 notes. So again, if I look at my formula sheet, arithmetic sequences, the explicit formula is given right here. So I'm going to use that formula. So I'm going to have a sub m. I'm starting off with 100 branches plus n minus 1. And I'm subtracting 3 branches every time, so that means my common difference d is negative 3. I want to know when or what level will have 67 branches. So this is telling me that a sub n is 67. So I'll have 67 equals 100 plus n minus 1 times negative 3. I'm going to use this equation to solve for n. My first step would be to distribute this negative 3. So I'm going to have 67 equals 100 minus 3n plus 3. So I'll have 67 equals 100 plus 3 is 103 minus 3n. I want to get 3n by itself, so I'm going to subtract 103 from both sides. And when I do that, I get negative 36 equals negative 3n. Divide both sides by negative 3, and I get n equals 12. So that means the 12th level will have 67 branches. John is about to turn 30 and wants to deposit his money each year on his birthday to save for retirement. He has 2 options he is considering. Write an equation for both options. Find the amount of money each option generates after 35 years. Circle the option John should pursue for his 35-year retirement plan. So this problem is having us do 3 different things. So let's see. Option 1 is buy a safe for his home and deposit $500 the first year and then deposit $1,000 each year after. Well, this is going to be linear. And I know that because I'm adding $1,000 every year. And whenever you have a pattern that's adding, that's linear. So I can use y equals mx plus b to write the equation, and that's the first thing that they want. So I'm going to have y equals, I'm adding $1,000 each year, and I'm starting off with $500. So $500 is my y-intercept, and then I'm adding $1,000 each year after that, so we'll multiply 1,000 for every year x. Option 2, deposit $3,500 into an investment account that earns 8% interest compounded monthly. This is going to be exponential because we know that the compound interest formula is exponential. And again, if you look at your formula sheet, that compound interest formula is towards the bottom of the page. I know that I'm using this because the problem specifically says compounded. So whenever it says compounded, I know I'm using the formula A equals P times 1 plus R over N to the N times T power. So this equation is going to be A equals, my principal amount is 3,500 times 1 plus 8% as a decimal is 0.08. If we're compounding it monthly, then N is 12. And again, we have notes on compound interest. You can go back and look at your Unit 3 notes for that. That's the first thing that they asked for. The second thing that they asked for us to find is find the amount of money each year, each option generates after 35 years. So here, that's going to be when X is 35. So I'll have Y equals 1,000 times 35 plus 500. And when you do that in your calculator, you should get $35,500. For option 2, oops, that's a 2, we're plugging in when T is 35. So I'm going to have A equals 3,500 times 1 plus 0.08 over 12 raised to the 12 times 35 power. And when you calculate this number in your calculator, you get $57,023.92. The third thing that they ask for is to circle the option that John should pursue for his 35-year retirement plan. So which option is better? To have $35,500 for retirement or to have $57,023.92 for retirement? Well, option 2 gives us more money, so option 2 is the winner here. Remember that exponential growth functions will always eventually exceed linear functions. The next one I was asked to look at was number 42. Here we're determining if this table is linear, exponential, or quadratic. There's lots of different ways that you could determine this. If you're having a hard time, focus on numerators and focus on denominators. If I focus on denominators, to go from 2 to 2, I multiply by 1. To go from 2 to 2, I multiply by 1. To go from 2 to 2, I multiply by 1. And to go from 2 to 2, I multiply by 1. If I look at my numerators, to go from 1 to 3, I multiply by 3. To go from 3 to 9, I multiply by 3. To go to 9 to 27, I multiply by 3. To go from 27 to 81, I multiply by 3. So we're multiplying each one of these fractions by 3 over 1. So my common ratio R is 3, because 3 divided by 1 is 3. When you have a common ratio, that makes this exponential. Explain, it has a common ratio. Another way we learned how to do this back in Unit 3, because this is a geometric sequence, you could take a sub 2 and divide it by a sub 1. So take the second term and divide it by the first term. And when you do that, you get 3. And then you could take the third term and divide it by the second term, and you'd get 3. Take the fourth term and divide it by the third term, and so on. So if you're getting stuck, you can also do it that way. These were the questions that you guys asked me to complete. I hope this information helps. As you have questions while you're working on this review, please let me know. I'm more than happy to help you get through it.